Hello, I'm Daniel Halmschlager from the research group Industrial Energy Systems. We're part of the Institute of Energy Systems and Thermodynamics here at TU Wien in Austria. In our research project Symphonies, colleagues from the AIT, the Austrian Institute of Technology, and TU Wien are working together to combine a set of up to now distinct optimization problems in the field of energy supply for industrial processes. What I would like to present in the next few minutes is an approach for combined optimization of heat recovery and thermal energy supply and show how it can be used in a small case study. But first, why is this important? At least in Austria, industry makes up for roughly a third of total consumed energy. The number in the EU is similar, and you can even find countries where this number is much higher. So if we want to reach our greenhouse gas emission goals, also industrial processes have to contribute to this reduction. This means that they have to become more energy efficient and shift to renewable sources of energy. And given that this is a topic of urgency, this shift rather has to happen radical now than gradually over many years. Shifting to renewable sources has a few implications though. The supply systems will have to become more diverse, so the one big gas-fired steam generator will not do anymore. Additionally, energy sources will become more volatile, and this also means that energy prices will fluctuate over time. And this means that the industrial energy consumers will have to become more flexible, which also means that their supply systems will become more complex over time. And this means that the operating and investment decisions will become more complex as well. The approach I'm now going to present addresses many of the points I just talked about. So how does our combined approach look like? In general, we take three distinct aspects of the system and optimize them simultaneously. The first is investment in the supply system, so the selection and sizing of units such as steam generators, thermal storages, solar cells, heat pumps, combined heat and power plants, and so on and so on. The goal here is to minimize the overall investment cost. The second task is typically called unit commitment and covers the operation of the supply system. So this means turning units on and off, selecting part load conditions, or charging and discharging storages. All this while considering the operating constraints of the system. This problem becomes interesting once your thermal or electrical demand changes over time and input factor prices such as fuel prices or electricity prices start to fluctuate. The goal here is obviously to minimize the total operating cost, including fuels and electricity bought from the grid, to satisfy a given electric and thermal demand. The third task is heat exchanger network synthesis, which deals with the optimal design of a heat recovery system. Here, decisions are made where to place heat exchanger, thermal storages, and heat pumps between the hot and cold process streams. In general, this is a trade-off between investment cost for the heat exchangers and operating cost for the utilities, and the objective is to minimize the overall cost. So what we've been doing is take these three tasks and model them together in one big mixed integer linear optimization problem. And additionally, we're considering retrofit scenarios, so cases where part of the equipment is already existing and can be reused. Not all of this is entirely new. We're building upon existing methods for simultaneous optimization of design and operation and the linear formulation of the superstructure in the heat exchanger network synthesis problem. What is new are the methods for selecting and sizing new, preferably renewable supply units, a linearized formulation for retrofitting heat exchangers, and of course putting all this together and applying it into a use case. More details on the exact methods I given in the proceedings paper, but now I want to jump into the use case to show you how it works. Our case consists of 9 hot and 8 cold streams that are active within different intervals in the covered 24-hour period. Additionally, we have a given electricity demand modeled after a German standard load profile for industrial processes and a given fluctuating electricity price. Finally, we have a set of fixed prices for the possible fuels, natural gas, biogas and biomass. Additional input factors are the investment cost for all the equipment, but listing these in detail would be too much for the scope of this presentation. As we are dealing with a retrofit case, we have an existing system where the thermal demand of the process is supplied via 3 temperature levels: steam, pressurized hot water and hot water by a natural gas-fired steam generator, a natural gas-fired water boiler and a natural gas-fired combined heat and power plant. The electric demand is supplied by the CHP plant and through the grid. Within our case, the steam generator and the water boiler are at the end of their service life and have to be replaced. Cooling for the process is supplied through cooling water. There is also a pre-existing heat recovery system consisting of 5 direct heat exchangers and 13 utility heat exchangers. The task for the optimization problem is now to find a new supply and heat recovery system without the end-of-life units, but possibly reusing the other existing components. The options we considered for the supply system were a biomass-fired steam generator, an electrode steam generator, an additional biogas-fired CHP plant, a high-temperature heat pump, an ambient air heat pump, a geothermal heat pump, thermal storages on all 3 temperature levels, solar thermal modules, photovoltaics, and a battery storage. And I will now jump directly to the solution and give you a little bit of data on the model itself afterwards. Out of the supply options, the solver selected a biomass steam generator, a high temperature heat pump, an ambient air heat pump, large area of solar thermal modules and storages on the low and medium temperature levels, additionally to the pre-existing natural gas-fired CHP plant. The optimal new heat recovery system consists of 13 new direct heat exchangers and 1 new utility heat exchangers. 8 of the previously existing heat exchangers are reused and shown in the chart in gray. For electric power, on the left side, we can see that the CHP plant can now run on full load, shown in light blue, for the full amount of time. And we can see that the heat pumps consume a large amount of electric energy outside of peak hours. For the heat demand, we see that the high temperature heat demand, the top part of the right chart, is only satisfied by the biomass-fired steam generator, as it is the only unit that can produce heat on this high temperature level. Excess high temperature heat is converted to medium temperature heat and used there. Most of the medium temperature heat is supplied by the high temperature heat pump while utilizing the medium temperature storage. For the low temperature demand, shown at the bottom of the right chart, we can see that the heat provided by the solar thermal modules, especially around noontime, is distributed through the full 24 hours by usage of the low temperature thermal storage. Now a few words about the implementation. The full problem was modeled in Python using Pyomo and solved in Gurobi on a bit dated 4-core i7 machine. The problem consists of around 15,000 decision variables, of which 4,500 are binary. We halted the calculation after 24 hours, where the solver was still at the solution gap of just below 6%. We recently recalculated the results with a new, much more powerful machine where we reached a similar solution within 1 hour and the actual optimum solution after 2 hours. But it then still took the powerful machine many more hours to rule out all the remaining nodes of the system in order to prove that this is really the optimal solution. So let's quickly sum up the results of the case study. I've already talked quite a bit about the new supply system and the new heat exchangers. But when looking at the levels of heat recovery, we see that the new system increases the heat recovery from 40% to 97% of maximum available heat recovery. This reduces the overall heating demand by over 40 megawatt hours or 38% within the covered 24-hour period. To conclude, we saw that the presented method can easily be applied to a case. We'd even say it provides a flexible framework to cover various retrofit scenarios. And, as seen in the case study, this actually works. Using this combined optimization approach, we are confident that we can reduce uncertainty in complex investment decisions for energy supply of industrial processes. Going forward, we are looking to further generalize the approach to become applicable for a wider range of cases. Another next step is to extend the problem through integration of production planning. As we use linearizations in many parts of the problems, we want to study the effects of those in more detail. And finally, although we are quite confident that the combined approach provides better solutions, we want to compare it to sequential solutions of the individual problems. Thank you for choosing to watch this video. Should you have any questions, please use the provided discussion groups or reach out to our group head, Professor Hoffmann, or myself. Goodbye.